I'm Antonio Sala, and in this video we are going to end our analysis of the covariance matrix structure of a Gaussian process. In a couple of previous videos we discussed how to represent this Gaussian process with some mean and covariance kernels, and then if the covariance matrix can be factorized like this, we can rebuild the variance structure given some latent variables, which are standard normal uncorrelated between them times this Q factor due to these identities here. If the matrix square root is obtained from the diagonalization, this is the matrix square root in this case, then the columns of Q are the so-called Carhonen-Loew eigenfunctions in the continuous time case, or principal components in the discrete multivariate statistics, and they have this kind of sinusoidal shape, and we devoted a video to analyzing the meaning of them. If we obtain a matrix square root which is lower triangular, then we obtained the so-called causal representation Cholesky factor, and if I plot the rows of this Q matrix, once some initial effects have vanished, all rows are the same, and the output can be expressed with a convolution formula, and each of these rows suitable displacing the origin to the first non-zero element in the diagonal end up being this convolution kernel, which allowed animating stuff so that my realizations of my random process were built, let's say, left to right, as the causal representation arising from the triangular stuff implied that one random variable only influenced the next ones on the list and not the previous ones, the past ones. So this is the animation of how the convolution kernel builds left to right a realization of my random process. Of course, this is zero mean and I would need to add the mean, but okay, that's standard stuff. However, we may think that apart from a lower triangular square root, as for MATLAB, my Gaussian process are just 241 random variables, I can just flip the order and say that now the first one is the last and the last is the first, or vice versa. I can flip rows and columns of the Q matrix, and if I suitably flip rows and columns of the original lower triangular Cholesky factor, then I get an upper triangular Cholesky factor that, again, it is a matrix square root of the covariance matrix, so it can be used to build new latent variables with a different interpretation. And which is the interpretation? Well, if I now plot the columns, then this will be an anti-causal representation. The first variable influences the first, the second variable influences the first and the second, the third latent variable influences outputs 1, 2, and 3. So one latent variable influences the past, let's say, variables and not the future ones. So that is anti-causal. But in statistics, as correlation covariance does not imply causality, the meaning of causal or anti-causal is just a matter of conceptually reordering my variables. If causality means something to me because I am exploring physical applications of these random variables, time series, whatever, then it's up to me. For MATLAB, there are 241 variables that can be arranged in any way I wish. So if for me I build them left to right, it was the previous animation, and if I build them right to left, then this is the other triangular factorization, and these are the columns of the anti-causal Cholesky factor, which are just the same ones as the causal one, but in reverse. So once we realize that, we can repeat the animation, so we will find the realization of my random process built right to left. Let's see. Here we have the right to left construction of my random processes that, okay, it may have an anti-causality interpretation, so that a variable influences the past and not the future, or just that, if I arrange variables in reverse, then I can explain equally how to generate a time series. For MATLAB, the order in which I arrange the random variables is irrelevant, as long as I switch the covariance matrix elements and covariance matrix factors accordingly. So this is the right to left anti-causal construction of a realization of my Gaussian process that appears in the bottom figure. And of course, I can also think of a reverse convolution kernel by just reversing the causal convolution kernel to the anti-causal stuff. So this will be the anti-causal factorization. But we have one more factorization. Let's see. Let us now consider the symmetric square root of my matrix, in which Q is equal to Q transposed, and it's V square root of the diagonal V transposed from the eigenvalues and eigenvectors from diagonalization. Indeed, if I multiply Q times Q transposed, which is the same as Q squared because Q is symmetric, so this is a true square root, then I get V square root of D V transposed times V square root of D V transposed, and as V is an orthogonal matrix, then this cancels out, this gets up being D, and of course then I have the covariance matrix K. So this is the symmetric square root of my covariance matrix, and then as the columns of the matrix square root Q illustrate the effect of each of the latent variables C, then let us plot some of the columns. And here we have them. They are symmetric. We have some initial and final deformations of the stuff, these finite window effects. But if we expand to plus infinity, minus infinity, our time domain of analysis, then we would have a so-called bilateral convolution kernel. In this way, in discrete time, in this way, in continuous time, indicating that each of the random variables affects both past outputs and future outputs. And in fact, it affects them in a symmetric way, as we can see here. So the way to build a realization will be multiplying each of these figures by a standard normal random variable, so somehow this bilateral representation with a symmetric square root is what I would call the hammer representation, in the sense that, okay, I may imagine that I have a plate of metal, let's say, and then with my hammer I hit here with a normally distributed force, so I get this deformation. If my normal latent variable is negative, then I hit through the other side and I get this deformation, a larger hit. Maybe another one will be hit with a smaller intensity, just depends on the random variable. So the superposition of these deformations of my metal plate due to my hammering on them with Gaussian hammer intensity would be the reconstruction of my Gaussian process. So if we simulate it with a random permutation in my hammer, Then we see the first component with this amplitude 1 scaling and the actual amplitude here. And then I throw the dice, my hammer deforms my plate, as we see in the bottom figure. Then my second hammer in here, then, okay, produces this deformation. Third hammering, fourth, fifth, each hammer produces deformation. So at the end, I accumulate hammering events and I build my realization in this symmetric causal plus anti-causal convolution kernel, or hammer deformation in layman's terms. So we'll run the animation until it finishes. I needed 241 hammer hits to explain the total standard deviation of my Gaussian process. So this is another realization, and to summarize all the collection of videos, in a stochastic process we can consider it a collection of random variables, and so the covariance between them is what defines the properties. And as that covariance matrix does have a lot of different square roots, then we have different interpretations on the meaning of the latent variables that build that covariance structure. We have the principal component diagonalization interpretation. We have the causal triangular square root interpretation, Cholesky. We have the anti-causal representation, the upper triangular flipping the order of columns and rows, and we have the symmetrical representation, the hammer on a plate representation, and all of them are correct from a mathematical point of view, in the sense that assigning importance to the flow of time left to right or right to left is physics, it's not statistics, in the sense that covariance, correlation, does not imply causality. So it is my knowledge on the thing that supposedly generates the data, the physics, that can tell me whether the causal interpretation is a good one, or the anti-causal if I am, receiving new data and filtering, correcting past estimations, or the bilateral, or whatever. I mean, all explanations of the variance, all the different structures for the latent variables, all of them are correct from a MATLAB matrix square root sense, and which one I choose for a particular application is my decision. So this is it. We conclude here. Thanks for watching.